we're going to be looking for divisibility tests for 7, 13, 17, 19 and so on. The tests we're familiar with from school textbooks all over the world, I expect, are 2, 3, 5, 6, 9 and 11. Those are the ones we have tests for. And some of the tests are simple enough. If a number is even, then it's divisible by 2, or to be more precise, if the units digit is 0, 2, 4, 6 or 8, the number's divisible by 2. So if I divide that by 2, I obtain 63 and no remainder. So we can say 126 is divisible by 2 with no remainder, or we can say 126 is a multiple of 2. The test for 9 is an intriguing one because it's very simple to perform. For instance, is 324 divisible by 9? We add 3 and 2 and 4, and in this case we do get a 9, so we know that number is divisible by 9. If we've got a number like 117, 252, then we just add the digits. 1 and 7 gives you 9, 9 and 2 is 11, 11 and 5 is 16, 16 and 2 is 18. So when you're adding the digits, you get a 2-digit number. Now, what we're actually finding has a special name. It's called the digital root, and it must be one single digit. So 1 and 8 add together to give you 9, so we know this number is divisible by 9. Had that number been 325, then we would have got a 10 here, and 0 and 1 makes 1, and that number, that digital root 1, would actually be the remainder on division by 320, division of 325 by 9. But I don't want to go into that any further now. We would like to know, why does this test work? Well, we've got 300, and that can be written as 99 plus 1. And we've got 20, which can be written as 2 times 9 add 1. And then we've got 4, which for the sake of the pattern I suppose we could write would be times 1. And when we multiply out these brackets, we're going to get 3 times 99 there, and 3 times 1, which I'm going to write here. Then we're going to get 2 times 9, and 2 times 1, which I'm going to write here, and then I've got my 4. So now we can see why this number must be divisible by 9, because 99 is a multiple of 9, so that must be divisible by 9. 2 9s must be divisible by 9, and as this adds up to 9, this one is divisible by 9 as well. So that's how the test works. Without using any algebra, you can generalize and see how it must work. So once again, if it had been 325, then this would have added up to 10, and when you divided 10 by 9, you would have had a remainder of 1. Now, the ones we're more interested in are the ones which are for 7, 13 and so on, and the primes must end in 1, 3, 7 or 9, because if they ended in 5 or 0, they'd be divisible by 5, and if they were even, they'd be divisible by 2. So we know that these are the only possible endings for prime numbers. Now, if it's a 1 that the prime ends in, or a 9, then the test is only a couple of steps away. So let's start with 31, that's convenient. And we've got two parts. We've got the units digit, and we've got a tens digit, and we're going to call that the operator because that's what we're going to be working with. So when we look first at a number like 434, this is a test that we do. Now I'm going to do it magically to start with. What I do is 4 3s are 12. I subtract it from 43 and I get 31. And that tells me that 434 is divisible by 31. Now that is quick. But what is going on? Well, actually I've multiplied 4 and 31 to give myself 124. So I'm actually subtracting a multiple of 31 from something that might be a multiple of 31, and when I do so I get something that is clearly a multiple of 31. That tells me that 434 must be as well. But because I can always be sure when I'm multiplying a number by 31 that the units digits are going to be the same, and when subtracted will end up as 0, I can forget about the final digit on the right, the final column on the right, and just work my way through to the left, which is what makes it swift and easy to do the test. 310 is obviously a multiple of 31, but if we have a 0 at the end of any number, it doesn't make any difference to the prime factorization of what is before. It just means we're going to have to add 2 times 5 to whatever the factorization of this number is. Well, let's take another one. Let's take 8215. Now, 5 times 3 is 15. Take it away, I get 806. 6 times 3 is 18. Take it away and I get 62. Then if I'm not happy, I can't see straight away that 2 31s are 62, I can say, all right, I'm going to apply the test again. I mark off the rightmost column. I say 2 times 3 is 6, and then that brings me back to 0. And 0 is a multiple of 31. So 8215 is a multiple of 31. And then I can do 16275. Not at all obvious that that's a multiple of 31, but let's apply our test. First of all, mark off the rightmost column and say 5 3s are 15. Then we're going to subtract 1612. Mark off the rightmost column, and we've got 2 3s are 6, which is going to give me, when I subtract, 155. Then I mark off the rightmost column and say 5 times my operator 3, 5 3s are 15, and that brings me back to 0. So there we are. That's the way that test works. But what about 41? Well, in this case, the operator is going to be 4. And I'm going to take the number 8692, ask myself, is that divisible by 41? And then I do the following. I mark off that rightmost column because I know I can neglect it. I know that 2 1s are 2, and when I do my subtraction I would get a 0 there. So 2 4s are 8, I put it there. 8 6 1. Now once again I'm going to mark off the rightmost column with the 1 in it, and once 4 is 4, and when I subtract that I'm going to get 82. That's neat. And then that's obviously 2 times 41, but if I want to complete the process I can say mark off the rightmost column, 2 4s are 8, and I get myself back to 0. So that's the test for 41, and I will do one more because we've got time to do that. 8102. Is that number divisible by 41? mark off that and give ourselves 2 as the rightmost digit. 2 times the operator 4 gives me 8, and that when subtracted gives me 902. Mark off the rightmost digit, which is 2. 2 times that operator 4 gives me 8, and when I subtract it I'm going to get 82 again, and I know that's a multiple of 41. So this works with 61, 71 and any number, any prime that ends in 1. But what about 7? Well, if we're working with 7, it doesn't end in 1 or 9, but we can simply multiply it by 3 and get ourselves 21. Now we can apply the same process, because we're going to be subtracting multiples of 7 from something that might or might not be a multiple of 7, and so we'll end up with one or the other. Take the example 4, 1, 3. Now I mark off that, and my operator is 2. So 3 2s are 6, and I subtract that from 41 and I get 35. That does the job nicely, because that's clearly a multiple of 5. Once again, if I'd done 3 times the whole number I'm using, 21, I would have had 63, and that would have all disappeared to naught when I subtract it, so I've got 35. What happens if I do the test again? Well, 5 times the operator 2 gives me 10, and when I subtract I get myself negative 7, which is a perfectly respectable multiple of 7. And let's have a look at one more. 1, 2, 0, 4. So this time I'm not going to mention the columns that are disappearing. I'm just going to say 4 2s are 8, which gives me 1, 1, 2. When I subtract, then I'm going to do 2 2s are 4, and I'm going to subtract that from 11, which gives me 7. So 1204 is a multiple of 7. So here are some nice tests, and they work very beautifully. You can, if you look at the left-hand side of this column, you can see that 7 can be multiplied up by 21 to 21. 13 7s are 91, which would give you an operator of 9, which is not too bad. 17 is multiplied up by 3 to give you 51, so you'd have an operator of 5. 19, well, that would give you an operator of 17, which is a bit awkward, but there's a much easier one if we're working with the final digit of 9. 23 would give you 116 as your operator. 31 gives you 3. 37 gives you 11. So these tests are, sometimes the numbers get a bit complicated, but when we come on to look at working with 9s as our final digit, we find that for 13 we've got an easier digit to work with, 4, for 19 2, for 23 7, for 29 3, and this will be explained in the next video.